Good day, Nixers. I am Errol, and once again, welcome to the Errol Electronics series, where we explore the world of electronics from the ground up. In today's session, we will be learning about the Bipolar Junction Transistor, or also known as BJT. Specifically, its constructional features, its operating principles, characteristics, and specifications, just like what we did on our discussion on diodes. Without further ado, let's start. To start our discussion about bipolar junction transistors, let's start with its constructional features, meaning what is its structure. For the constructional feature of a BJT, we have to emphasize that semiconductor devices are primarily made by combining an N-type and P-type semiconductor materials. Now, in the case of a BJT or bipolar junction transistor, so we have two types. We have an NPN, meaning it has two N-type and one P-type, or a PNP, two P-type semiconductors and one N-type semiconductor. Now, for the purposes of our discussion today, and also for us not to get confused of these two types of BJT, we'll just focus our attention on the NPN type transistor. So shown here is an NPN type transistor. So we have a P-type semiconductor material sandwiched between two N-type semiconductor materials. Now, just by looking at this constructional feature or structure, we will be able to decode or say that there are three terminals for our transistor, unlike a diode that has only two, the anode and the cathode. So in this case, we have three terminals. So what are these three terminals? So we have the collector, we have the base, and also lastly the emitter. So these are the three terminals of our BJT. Now, for the features or the characteristic of these three terminals, so we have, in terms of physical dimension, sa physical meaning the size of these three terminals, the collector is the largest, or meaning the thickest of all these three semiconductors, followed by the emitter, and the thinnest, or yung pinakamanipis, is the base. Now, in terms of doping levels, emitter is the most heavily doped. Next it is followed by the collector, which has a doping level that is in between the emitter and the base, and the most lightly doped material is our base. So madali lang matandaan yung base. It is the thinnest in terms of physical dimension, and it is also the lowest in terms of doping levels. But you need to understand that there is interchangeability, or there is a difference between physical dimension and doping levels for emitter and collector. Now, in terms of the actual photo of this particular semiconductor device, so we have this example for a BC547 BJT. So this is its form. So this is also an NPN type transistor. So we have here the three terminals or three leads, or another term for leads is pin out, three legs. Ayan, we have the three terminals, the collector, the base, and the emitter. So this particular packaging is known as TO92, Tango Oscar 92, this particular packaging. So mga transistor, merong kanya-kanyang forma, at yung tawag natin sa forma na yon is yung kanyang packaging. So ito ngang, this particular transistor is actually in TO92 packaging. This part over here is actually the schematic symbol for our NPN transistor. Now, NPN transistor is different from PNP in the sense that the diode, or this particular arrow here, is pointing away from the base. So that is the characteristic of an N-type or NPN transistor. Okay? Now, what happens when the N, P, and N first meet? Okay? When N combines with P and N combines with P. Okay? We have already seen this in a diode. So what about for a transistor? So let's find out. Okay? So once these, okay, two materials merges with a p-type semiconductor, okay, so there will be a junction that will be created just like for a diode, and just like for a diode there will be a depletion layer, okay, because of the recombination of the holes and electrons in this particular part of the junction. Okay, now, so meaning this particular BJT is actually made up of two diodes. We have this PN junction over here. So this is one diode. And this is another junction over here, PN. Okay, this one. Okay, so we call this the emitter base diode, or simply the emitter diode. And dito naman, okay, this is the collector base diode or the collector diode. Okay, and each of the junctions have its own depletion layer. Okay, so that will be for the constructional feature of a BJT. To start the discussion about the operating characteristics of our bipolar junction transistor, okay, let's first know the roles that each of the terminals play. Okay, just like in a game. So, for example, nito class is the game Dota. So, alam natin that when we play this particular game, there are particular roles that the players need to play. Okay, we have the carry, the support. So, if the support will not play this particular role and, okay, instead play as carry, so it will be detrimental to the whole team. So same with the BJT, same with the terminals of the BJT. Okay, there are certain roles that these particular terminals needs to play in order to provide the needed, okay, yung function nga ng BJT is to function as a switch or as an amplifier. Pero yung pinaka-basic niya na function is to become an amplifier. And we will actually see that in the roles that these terminals play. Okay, so first of all, on the roles of the terminals, okay, the emitter, since it is the heavily doped part of our transistor, okay, it emits the electrons. And these emitted electrons will go to the base and will be injected to the base. It's very important yan that the emitter emits and injects electrons to our base. Now next is the base will pass these injected electrons to the collector. As we have learned kanina, or as we have discussed earlier, okay, the base is actually very thin, okay, permitting that the electrons that passes through it will be able to pass through to the collector. And the collector, as its name suggests, will collect these injected electrons on the base. And these are the roles that these particular terminals play. And that is why it actually contributes to the amplification effect, okay, of this particular semiconductor device. Okay, so let's watch a video for us to be able to appreciate this particular roles that these terminals play for our transistor. Okay, here we see a battery connected to the collector and emitter of our transistor. Now, if we take a look at here, there will be no flow of current since one of the PN junctions will be reverse biased even if we interchange the connection of our battery. That's why there is a need for another circuit in our base and emitter terminals. Okay, we have this battery and resistor connected to the base and emitter, okay, which allows the emission of electrons towards the base. So, i-inject niya ngayon yung electrons, and these electrons, part of that, a very minimal number, will be attracted to the positive terminal of our first battery. Okay, will be attracted, so there will be minimal amount of current, but majority of the electrons will be collected by the collector terminal and will be attracted to the positive terminal of our second battery. And that's the time there will be flow of electrons, okay, from emitter, base, then collector. And there's amplification factor as we can observe here. Okay, collector current, okay, makes the load brighter, emit more light compared to the bulb on the base. Okay, and beta is our amplification factor. Basically, that means that if beta is 100, meaning our collector current is 100 times that of the base current. This is when, okay, we interconnect the actual transistor. For the characteristics of our bipolar junction transistor, okay, so we have to consider two, okay, diodes. Okay, the first one is the base to emitter diode, or what we call the emitter diode, as shown in this circuit. Okay, so this is the first, okay, characteristic curve from base to emitter. Okay, and as what we can see here, we have our source, okay, represented by the variable VBB. Okay, we have also our resistor, base resistor, which is 100 kilo ohms. Okay, and we have, okay, even though it is not written here, but it is understood that there is a voltage drop across the base to emitter. Okay, and that voltage drop, since this is silicon transistor, okay, this will be 0.7 volts. Okay, so as what we can see here, the characteristic curve of the base to emitter is actually, okay, mapapansin nyo dito, this is actually similar to a diode characteristic curve. Okay, so there is this knee voltage at 0.7, current will start to, okay, surge, okay, or to rise up rapidly, okay, indicating that there is a flow of current, okay, after it reaches the knee voltage, for this particular potential barrier of our base to emitter. Okay, so by KVL, okay, applying Kirchhoff's voltage law for us to be able to solve for the current IB, okay, so we have, if we establish a current in a counterclockwise manner, since this is the negative part of our battery, and we know that electrons will start to be, okay, there is a surplus of electrons here, so it will repel the electrons in our conductor. Okay, it will repel the electrons in our conductor, and then, okay, since it is greater than our potential barrier, which is 0.7, okay, it will also repel the electrons here, permitting a flow of current in this particular circuit. Okay, so it will be a positive VBB, okay, then minus a minus VBE, then minus also the resistor voltage. This will be our equation. VBB minus VBE minus VRB is equal to 0. Okay? Now we will transpose this part. Okay? Since alam natin that this is 2 volts, alam natin that this is 0.7 volts, ito, hindi natin alam. So we will be transposing it to the other side. This will become positive. Okay? And this one is actually the product of the base current, the current that flows through the circuit, okay, times the resistor, RB. So we will be, okay, we will be splitting this up to I and R. Okay, IB times RB. So dividing by RB both sides, since RB is given, okay, so we will be able to solve the base current, which is equal to VBB minus VBE all over RB. Okay, and this is the equation for our base current, or the current that flows through the base of our transistor. Now moving on to the other side, or the collector loop, or the collector curve of our transistor, okay, we have the IC versus VCE characteristic curve, or basically the current in our collector circuit, okay, and the voltage across the collector and emitter. Okay, so as what we can see here, okay, less than 1 volt, the voltage of less than 1 volt, probably around 0.2 volts, okay, the current or the collector current rises up rapidly up to the value of equal to 1 milliampere. Okay? It rises rapidly. When VCE is 0.2 volts, it rises rapidly until it reaches 1 milliamperes. But even if we increase the value of VCE or the collector to emitter voltage, okay, as we increase the collector to emitter voltage, our collector current remains constant. Okay? So this is the characteristic of our transistor. Okay? Even if we increase the collector to emitter voltage, the value of the collector current remains constant. Okay? But as we reach 40 volts, which is what we call the breakdown voltage for our transistor or the VCE max, yung specification of VCE max, then that's the time that our transistor will break down and will be damaged. Meaning it will no longer function as a transistor with its amplification effect. Now, what I want you to notice here, class, is the value of the base current. Supposing that our base current is 10 microampere, so this symbol is micro, 10 times 10 raised to negative 6, okay? So 10 microamperes. The value of our collector current will be 1 milliampere. So that's basically 100 times our base current. Since if we multiply 10 by 100, that will become 1,000. So 1,000 microampere is just the same with saying 1 milliampere. Okay? So in this case, okay, the beta value or the amplification factor or the HFE of our transistor is equivalent to 100. Okay, so that's basically the amplification factor, meaning the base current is very minimal, micro in units of microampere, but we are able to produce a milliampere range current on our collector circuit. So that's basically what this characteristic curve says. Okay. So now what we have discussed so far is for a base current of 10 microampere. But what if we increase the base current? Okay. We play with the base current or we play with the base voltage, yung VBB natin, okay, and arrive on a different value of a base current. What happens to the collector current? So shown here are a set of collector curves. Okay, meaning, okay, if our base current is 20 microampere, we will be able to arrive at a collector current of 2 milliamperes. Okay, if we have 30 microampere of base current, we will have 3 milliamperes of a collector current. What this set of curves basically mean, this set of curves is actually for only one transistor. This basically means that as we increase the base current, okay, we also increase the value of our collector current. Okay, since the base and the collector are related with the beta value, okay, especially on the amplification. Okay, so that's basically why we have this particular set of collector curves. Okay, okay. So meaning we can alter, okay, we can play with our base circuit, okay, such that we will be able to produce 10 microampere. So for example, our RB is 100 kilo ohms. We have our VBE that is constant, which is 0.7. So all we need to do is to calculate or play with the value of our VBB such that we will be able to produce a current that is 10 microamperes. And from there, okay, we'll be playing with the collector voltage such that we will be able to, okay, bias this part of our circuit in a manner that we will be able to produce the 1 milliampere amplified current. Okay, so that's the characteristic of our, okay, BJT. So basically, there's an amplification. A small base current translates to a high collector current. So shown here is the specification sheet of transistors BC546 to BC550. Now here we are concerned with the specification of the transistor BC547 as we have used this as an example a while ago. Okay? So here we see the packaging of this particular transistor. So it's TO92 as what we have said earlier. Okay. So for a TO92, facing the flat rectangular part of this particular transistor, okay, the leftmost leg or pin out will be the collector, the middle part will be the base, and then the rightmost leg or pin out will be our emitter. Okay. Now we have here, just like with the diode, transistor also have absolute maximum rating. Okay. And the first one is VCBO. This just means that this is the voltage between the collector and the base with the emitter left open, meaning hanging yung ating emitter. There's nothing that is connected to the emitter, only a voltage between the collector and the base. And the maximum voltage that it can withstand will be, for BC547, this one, it will be 50 volts. Okay? For VCEO, this means that this is the voltage from collector to emitter with the base left open. Okay? So the maximum voltage that it can withstand is 45 volts. Above that, our transistor will break down. And the voltage between emitter and base with the collector left open. So O here stands for open. Okay? With the collector left open, okay, for BC547, that would be just 6 volts. Okay? So we move on to the electrical characteristics. Okay? So here we see the HFE, or the transistor's beta value, the amplification factor, or the DC current gain. So here we see that there's a minimum of 110 and a maximum of 800. Okay? So this is the beta value for these transistors. Okay? We have also this VCE SAT and VBE SAT. Now, for this particular instance, okay, let me just emphasize that these values, yung may SAT, okay, meaning yan saturation, this means that these are the specifications when our transistor is used as a switch. Okay? So we have not yet discussed the working of a transistor as a switch, but if we do, okay, go to that particular area, okay, of a transistor's working condition or function as a switch, okay, then we will be using these particular values, the VCE SAT, okay, the voltage across the collector and emitter during saturation, and the voltage across the base and the emitter during saturation. Okay, and the values of this is 250 millivolts or 0.25 volts. Okay, for the VBE SAT, it is 700 millivolts or 0.7 volts, just like for a silicon transistor. And here we also have the VBE on, a base emitter on voltage. So we have the maximum of 700 millivolts, typical 660 millivolts, and minimum of 580 millivolts. So I've highlighted here that for silicon, it's 0.7 approximately. Okay? Ayan. And all other, okay, electrical characteristics or specification. So those are the specifications of our transistor. Now, take note of this particular given here, that the temperature, okay, is actually 25 degrees Celsius unless otherwise noted. So these particular values is for an ambient temperature, T sub A, of 25 degrees Celsius. Okay? So these are the specifications of our transistor. Just like for a diode, it has its own specifications. Transistors also have its specifications. Now again, this will guide us towards the specifications or the values, the parameters of our transistor, such that we will not be able to damage our transistor. And that ends our discussion for this session. If you found this video helpful, please leave it a thumbs up. Subscribe to this channel if you are not yet subscribed, and ring the notification bell so that you will be updated on our latest uploads. And as always, I'll see you on the next one.